Alright, let's get started with this problem. This is LeetCode number 692, top k frequent words. Given an array of strings, words, and an integer k, return the k most frequent strings. Return the answer sorted by frequency from the highest to lowest. Sort the words with the same frequency by their lexicographical order. And the follow-up is, can you solve it in n log k time and O of n extra space? Well, the first thing that comes to mind is to use a heap. I think that when we're talking about getting the top k elements, I think it's pretty natural to say that a heap approach is the most straightforward, simply because of the way that the heap invariant works. It is very efficient to sort elements when you place them inside. And in this case, we know that there will be at most k words, at least that there should be at most k words, k unique words. Let's see. There will be at most k words within the array, the input. Sorry, I don't know why my mind is blanking. And so when we call heapify, I know that heapify, if we're talking about just plain old heapify, then it should be somewhere in the realm of n log n. I'm just trying to think about how we can justify it as n log k. But I suppose that if we're operating on all the elements, that there's our n, and then our log k comes from potentially popping the elements or pushing the elements in. I have to think about that a little bit more, but let me get my thoughts on paper in terms of what I think is a reasonable first approach. So we can start by creating a frequency map of each unique word. So this would be a mutable map of string to int, where int is the frequency of the string. We know that the word only consists of lowercase English letters, so we don't need to worry about case sensitivity here. Then, for each element within the frequency map, add the item into the heap, where this is a max heap. And then for 0 to k minus 1, pull an element from the heap. So this initial frequency map will use O of n time, O of n space, assuming that each word in our words list is unique, and n is the number of words within our list. Realistically, this might be bounded by k, where k is the number of unique strings. So n is the number of words within our input. K is the number of unique, let's make this capital, words within our input. Of course, we need to iterate over all the strings within our input, but we only store k strings where k is the number of unique strings. K may be at most n. Then within this frequency map, this will be O of k times, at most we have O of k layers, or log of k layers. So this becomes O of k log k. At least I think so. And since we're removing the elements from our map and adding them into our heap, then I don't believe that we have any additional. Well, we're going to need a way to store the string and the frequency, right? Within a single entity of sorts. So that might require O of n space there, or O of k space, again. And then this will just take O of k time. Well, this will also take O of k log k, right? Because we need to go through k elements, and each polling will take log of k time. Because for a heap, you swap it with the last element, and then you bubble it, and that sort of thing. So that will take O of k log k time as well. I'm curious as to where the O of n log k within this example comes from, and where this O of n extra space comes from. But I think this is a reasonably close enough sort of approach. So I think with that, I am going to get started with coding. So first we're going to have to deal with later on with our heap. So let's create a data class. We'll call this heap node, which has a val string, which is a string, and a val frequency, we won't be changing this, which is an int. We'll also create a class heap compare, comparator, we'll call it. If I implement comparable here, then I override the function compare to. And this should override compare. Or implement heap node. Other, which is a heap node. And let's say if I compare this to the other, we'll say return when, and this should be returning an integer. This dot frequency is equal to other dot frequency. This will return 0. This dot frequency is less than other dot frequency. Since we want this to be a max heap implementation, we want this one to be greater, right? And we can throw an else case in here. Because typically we want this to be, when we want it to be a min heap implementation as it is by default, then this value, since this frequency is less than this one, so this minus the other should be a negative number, right? But in this case, we're going to be flipping it. So hopefully this overriding of compare to will actually allow us to add it into a heap without much trouble. Let's create our map now, which will be a mutable map of string to int. And then we'll say words for each word. And we'll say let's see, frequency map, put into there a frequency map get or put our string, or rather our word, otherwise put a 0 in there. we need to cast this as a... Actually, we shouldn't need to cast... Well, let's cast this just in case. +1. So we will put into the word key the value at the word or 0, cast it as an integer, and add 1 to it. So now we can say frequency map for each entry. And we'll need to create a heap here as well. This is a priority queue as a concrete implementation of heap node within the JVM. We will say heap dot push or add a new heap node which has an entry a value of entry dot key and a frequency of entry dot value. And then for I in 0 to k minus 1, because it's inclusive, frequency or val return list is a mutable list of string return list dot add we want a heap dot poll, which will return us a heap node dot string, and then we return our return list. Cool. Let's see. So we start by or turning everything into our map, and then we'll move all those elements within our heap, and then we move those elements within our list, and then we return that list. So it's not particularly memory efficient because we're sort of running 3 times the values that we need in terms of our space, but we'll see. So it looks like it worked for the first implementation or the first test case. Let's see if it works for the second test case. Looks like it does. Let's see. The problem really then comes down to the fact that we don't really have a proper way of sorting elements, right? So our new problem is sorting elements which have the same frequency. Let me think about this. Tea leaf fragments. Not going to be able to drink that for a bit. Same frequency sorting. We can create an auxiliary list and sort and just call a sort on that. Though that wouldn't necessarily be very efficient. Maybe there's an invariant that we can get in a different way. If they are the same frequency, What happens with heaps when they have the same value within a comparison? They just don't move, right? They just don't bubble up. Right, because they're added at the end, and then they bubble up to where they need to be. And if their parent node is... So here's what I'm thinking. So the problem is that we need to also consider the lexicographical ordering of the items. What I'm thinking in terms of the solution we let the heap do the work for us. So let's assume by default the heap preserves insertion order if there are no other or if the comparison is equal. Which means that if an item is added at the end of the, or at the bottom of the list in the last place where it could go, and the element above it is equal to it within the comparison, then it will stay where it is without swapping. However, we could also add into our compare to overload that we want to consider also the lexicographical order of the string. Thus, when pulling out elements from our heap, we get them in the right order. So currently we don't have this particular ordering in place. So we should actually get the first example wrong now that I've swapped the ordering, right? Right. So now what we want to do is that we want to go up here and say here. So if they have the same frequency, we also want to compare the strings. Let's see. If this dot string is less than other dot string, return -1. Else if this dot string is greater than other dot string, return 1. Else return 0. So actually we can just do this, I think. Let's see. Because we want the lexicographical ordering, right? Actually, can we just do this dot string dot compare to other dot string? I wonder if string in the JVM implements comparable. At least in the way that I want. Okay, I think it does. Let's see, string comparable. Lexicographically. Okay, awesome. So yeah, this should actually work. So that's the additional problem solved there. So now if they have an equal frequency, we compare them lexicographically so that we move the item that is the same frequency but lexicographically lower, so closer to A, I believe, first, at least with the lettering, right? So we would pop that out first. Let's just make sure that we didn't regress by running the original test cases. And let's throw in a submission and let's see if there are any edge cases that we missed. Okay, looks like it worked fine. That was a surprisingly quick problem, but hey, heaps are awesome. At least when you get them to work. In any case, I hope you learned something, and I'll see you for the next problem.